One of my favorite questions to revise the topic of acid and base and to revise titration curves. So first of all, let's understand which type of titration curve this is. We're looking at methanoic acid and sodium hydroxide, meaning that it's a weak acid, strong base titration. And this should give us already many information because this is one of the very particular ones that gives us really many chances of calculations and analysis. So first of all, we know that it has a pH of 2.2, so this is going to be our starting point. Then we know that 20 centimeters cube of this solution, so we're talking about the acid, is titrated with 0.1 sodium hydroxide until excess is added. Okay, so there are a few things that we need to find in order to plot this titration curve. So we're going to need the volume that is added of sodium hydroxide, so we're going to need to calculate that. Okay, and then we also need to know the pH at the end of titration. And we need to find the pH at when we have in excess sodium hydroxide. So as you can see, many calculations that we get the chance to do. So for the volume of sodium hydroxide, please don't be thrown off by these calculations because it's just a mole ratio calculation, really. We know sodium hydroxide and methanoic acid, they react by 1-to-1 ratio. So methanoic acid, I'm going to write it as HA. Okay, so this is going to form NaA plus H2O. So as we can see, it's a 1-to-1 ratio. So if we have a 0.1 molar of the acid and 20 centimeters cube of it, okay, how much of the sodium hydroxide that do we need? Oh, no, sorry, this is 0.2. If we have 0.1 mole per decimeters cube, I mean, you can do the calculation, but I hope you can see right away that we're going to need double the volume to neutralize it. In fact, it's going to be 40 centimeters cube. Okay, so 40 centimeters cube. Now, there is one important information that we don't have in this case, but if we have it, could be very useful to plot this perfectly, which is the Ka. Let's say the Ka of this is 1.45 times 10 to the minus 4. This would tell us something very, very important for an acid and base titration, because the pH at half neutralization point is equal to the pKa. Okay, so half neutralization point, this is when the concentration of HA is exactly the same as the concentration of A minus. So if we look at the Ka, that is going to be H plus A minus. So do you see how if we have exactly the same concentrations, these two cancel out, so we have the same concentration of H plus. I know this may be confusing, but so what is it, the half neutralization point? Yeah, it's because you have perfectly this 1-to-1 ratio, yeah, between this and this. Okay, so this is going to be 1-to-1 ratio. So I hope you can understand it chemically of how these two things react together. Okay, and so if we had, this is the case, it's going to be 3 point something. So I know that at half neutralization point, so around 20 centimeters cube, I'm going to have like a 3 point something. As you can see now, we have already two kind of points that we can plot. Okay, maybe we could do a little bit better, obviously, but something like that. Okay, then we can calculate the pH at the end of titration. This we know that the pH is going to be above 7. Why? Because it's a weak acid, strong base titration. So this is something to know. And we will also explain why. And then the pH when we have excess sodium hydroxide. Now, how do we calculate that? Kw. Okay, so Kw, of course, is equal to H plus times H minus, or OH minus. And if we wanted to calculate the concentration of H plus, we just rearrange it to do Kw divided by the concentration of OH minus. Now, that's something that we need to calculate. I will let you do that because this is not required for these questions. It can just be an approximation. But again, like this, you can see that it's going to be a pH around, between 13, something like that. Again, if you want to plot this perfectly, I invite you to calculate that. Okay, so around 40, we know that it's going to go like that, maybe a little bit more flat. Okay, and then we know that it's going to be a steady increase until 40. Okay, so as you can see now, we can extrapolate, yeah, the half, and we should have 1, 2, 3, kind of 4 boxes. So around that, let's say between 8 and 9 is going to be the pH at end point of titration. Okay, this is something that I really want us to work out, because one of the very common question is why the pH is above 7 at end point of titration. Okay, and this has to do with what is present at equilibrium. Okay, so let's focus on this reaction that I wrote up here. Okay, and let's think about that at equilibrium, so not at equilibrium, sorry, at end point of titration, we have the salt present. So this salt, yeah, notice how it's a reversible reaction. So basically this salt can just be hydrolyzed further, okay? So can react further with water to form, guess what? Back the undissociated acid and sodium hydroxide. But sodium hydroxide, it will always dissolve. So because the equilibrium was shifted to the left-hand side because the salt is further hydrolyzed, it would release a little bit of hydroxide ion in solution. And that's why and that's why endpoint of titration would be above 7. So it's because of the conjugate base. Yeah, the conjugate base hydrolyzed further to reform sodium hydroxide, which will release a hydroxide ion. There is another part that I love about this question, yeah, and specifically acid and base titrations, which is this. So this, do you see how the pH, okay, sorry, it's really not the best curve that you could write, but you get the idea. It's the buffer region. Why is it a buffer region? So now, whenever you have weak acid and base, the bell of buffer should ring. Because if we have excess acid plus, guess what? It's salt. What is this? It's a buffer. And where does the salt come from? It comes from the reaction from a base and the acid. So remember that if we want to do buffer calculations, we know that the moles of sodium hydroxide are going to be exactly the same as the moles of the salt. Yeah, because the salt, yeah, it comes from the reaction of the acid and sodium hydroxide. So this is the buffer region. Why? Because we have excess weak acid with the salt. Okay, so please always recognize weak acid and base. Ooh, buffer, very important. So as you can see, this type of question can lead to many different type of calculations, and this is what we can expect in our paper 1. If it doesn't come out in paper 1, well, maybe paper 3.